Okay, in this video, I'm going to look at confidence intervals. This may be a little bit of a repeat from other videos I've shown you, but we're going to start with confidence intervals and estimation. It shouldn't take us too long. So the assignment of values to a population parameter based on the value of the corresponding sample statistic is called estimation. So rather than just read these to you, let me explain what I mean by that. That we want to estimate a population proportion. We don't know the proportion of the population who all feels on one way on a particular subject. You do a sample of 200 people, 1,000 people, you get your sample statistic, your p-value. Later in this video, you'll get an x-bar value, and you use that p-hat or you use that x-bar to estimate p or to estimate mu. We'll also look at the difference in proportions, the difference of means. So this process of estimating the value, shockingly, is called estimation. Okay, a little vocabulary that should make some sense. The value that you assign is called your estimate. The value of the statistics that you use is called the estimator. And here's the process. You select the sample, collect your required information, calculate the value of the sample statistic, and then you use that to estimate the population parameter. Two types of estimates we're going to look at, a point estimate, an interval estimate. And again, this is going to seem a little bit repetitious from things you've heard from me. Please stick with it because I'm going to move beyond where I've been in some previous videos. So a point estimate and interval estimate. Okay, so the value of the sample statistic is used to estimate a population parameter, and that's called the point estimate. Okay, we're also going to have a margin of error that we're going to use when we calculate the population um, parameter, but also the interval estimate when we do that. So interval estimation is what is going to take the most effort here to explore. We've looked at this before. Our confidence interval is our point estimate plus or minus our margin of error. This PowerPoint slide that I'm using here sets up the formula a little bit differently than I do. You'll see in the whiteboard section on the left that I'll write these things a little bit differently. Okay. So population proportion, we start with P. We find the standard deviation of P hat, the square root of P hat, um, 1 minus P hat, which I call Q hat, over N. Okay. So again, here you'll see P hat plus or minus Z sub Z S sub P hat. This here is our margin of error. Notice the margin of error E is Z times S sub P hat. Okay. And here's the formula. S sub P hat equals the square root of P hat Q hat over N. So let's look at an example. And for each one of these parameters, there's 5 parameters. I'm going to give one example. So I will be doing 5 examples. So according to a Rasmussen poll from 2017, December of 2017, 35% of Americans feel that the country is going in the right direction. Rasmussen surveyed 2,500 people. Let's write down some information first. So Rasmussen, let's not do green, let's do black this morning. So Rasmussen surveyed 2,500 people, and P hat, the proportion of people in the sample who felt that America was going in the right direction, was 0.35. Okay. Number one, what's the point estimate for P? This is complicated. Don't lose this. If P hat is 0.35, our best estimate for P is that P is approximately 0.35. And there's your point estimate for P. Okay, so that shouldn't be horrible. Number two, what's the interval estimate for P? Okay, now to find the interval estimate for P, remember that P, the interval on which we'll find P, P is going to be somewhere between P hat minus our margin of error and P hat plus our margin of error, where the margin of error is Z sub C times S sub P hat, and S sub P hat is the square root of P hat Q hat over N. Okay, so I know that P is somewhere between 0.35 minus the margin of error and 0.35 plus the margin of error. Okay, so let's figure out the margin of error. Now, we want a level of confidence of 95%. Recall, therefore, that the Z value is going to be 1.96 times the square root of P hat Q hat. If P hat is 0.35, Q hat is 0.65, and we divide that by n. Okay. So now we use our calculator. I do not have a calculator again on this computer, so I'll let you, excuse me, I'll let you calculate that on your own as I do it as well. 1.96 times the square root of 0.35 times 0.65 divided by 2,500. And I get a margin of error of 0.019. And I'm going to go 3 decimal places. So that's my margin of error. So P then is going to be somewhere between 0.35 minus 0.019 and 0.35 plus 0.019. So 0.35 minus 0.019 is 0.331, less than or equal to P, is less than or equal to 0.35 plus the 0.019. So that's 0.369. And here is my interval estimate. You're also going to want to be able to translate that into words. Based on the Rasmussen poll, we would estimate that approximately 35% of Americans in 2017 felt that the country was going in the wrong direction. But that would be 35% plus or minus 1.9%. So in other words, somewhere between 33.1 and 36.9% of people felt that the country was going in the wrong direction, and we're about 95% confident of those results. Excuse me. So let's move on. What if we want to look at the difference in two sampling proportions? Okay. So now we're going to have a P1 and a P2, a P hat 1 and a P hat 2. Certain conditions need to be met. Okay. Your proportions need to be, the difference needs to be approximately normal. There are a couple conditions where you can see that this must be true. Okay. NP, NQ, NP, and NQ for both variables, they must be at least 10. Okay. So make sure that the product of those is at least 10. And here are the formulas. The only thing that changes is notice that the standard error is no longer the square root of P hat Q hat over N. It's the square root of P hat Q hat over N1 plus P hat 2 Q hat 2 over N2. So just a little bit of extra work to do. And the mean, notice there is P1 minus P2. Let's do an example. According to a July 2009 Quinnipiac University poll, 62%, let's go with, there's going to be adults age 18 to 34 and 35 plus. So the young group, I'm going to call group 1, and the older group, I'm going to call group 2. For the younger group, age 18 to 34, 62% of adults in the age group from 18 to 34 and 50% of adults in the age group 35 and older surveyed believe that it's the government's responsibility to make sure that everyone in the United States has adequate health care. Okay. In the younger group, there were 683 people surveyed, and in the older group, 2,380 people were surveyed. Okay, so find the point estimate for the difference in those proportions. Now, group 1, I'm going to call this P hat 1 and N1, P hat 2 and N2 for the two different groups. Now, P hat 1 minus P hat 2 is 0.62 minus 0.50, and that's 0.12. Therefore, the difference in my sample proportions is 0.12. The difference in my sample proportions is 12%. The difference in my population proportions then would be approximately 0.12. I would assume that since the difference in the sample proportions is approximately 12, it is exactly 12%, the difference in the population proportions would be approximately 12%. Positive because the first group, the proportion is greater. Okay, so there's my point estimate for the difference in the proportions. Now find the 95% confidence interval for the difference in those two proportions. Again, P1 minus P2 is going to be somewhere between the 0.12 minus margin of error and 0.12 plus the margin of error. To calculate the margin of error, it's still Z sub C times S sub P hat. What's going to change is not the Z, but how we calculate the formulas aren't going to change other than for S sub P hat. We want to be 95% confident, so our Z score is still 1.96. Now, instead of just subtracting or multiplying by the square root of 0.62, 0.38 over 683, which is P hat 1, P hat 1, Q hat 1 over N, underneath that radical, we need to add the second set of variables, set of values, which is P hat 2, Q hat 2 over N2. Okay, and that's now what I'm going to calculate in my calculator, and I would encourage you to do the same thing. So that's going to be 1.96 times the square root, 0.62 times 0.38 divided by 683 plus 0.5 times 0.5 divided by 2380, and we get E is equal to 0.042 if I round that to 3 decimal places. So we have a margin of error of 0.042 or 4.2%. So then our P1 minus P2 is going to be somewhere between 0.12 minus 0.042 and 0.12 plus 0.042. So we would estimate that the difference in the proportions is somewhere between 0.078 and 0.162. So the difference in the proportions, the interval estimate, is somewhere between 7.8 and 16.2. The proportion of younger adults who feel that it's the government's responsibility to make sure that everyone in the United States has adequate health care. The proportion in the younger group that feels this way is somewhere between 7.8 and 16.2% more than those who feel that way in the older group. Okay, so I hope that that example makes a little bit of sense there. Let's move on and look about what about a sampling mean? So in a sampling mean, it's going to be very similar, except that we're going to use mu and sigma for mean and standard deviation. Okay, the standard deviation formula, though, is a lot easier. Sigma divided by the square root of n. However, just like in the proportions, when I don't know p, I estimate p with p hat. I don't know sigma, I'm going to estimate sigma with s. I do believe, though, in these examples, we might say somehow we know sigma because there is another adjustment that we'll talk about in future classes, future videos about what to do in that adjustment. Okay, some conditions. The population needs to be bell-shaped or normal. If the population itself is not bell-shaped, but you take a large random, we would expect that a large random sample, we would expect that the sample is going to be normally distributed, even if the population is not. Okay, so standard deviation, sigma over the square root of n. Therefore, the standard error of x bar is s over the square root of n. Okay, notice that this slide looks very similar to what we've seen before. Mu is going to be somewhere between our margin of error confidence interval, x bar plus or minus z times sigma sub x bar. This is a margin of error. Mu is somewhere between x bar plus or minus margin of error. Okay, so in other words, mu is going to be somewhere between x bar minus a margin of error, x bar plus a margin of error. We calculate our margin of error, z sub c times sigma sub x bar. Sigma sub x bar is sigma divided by the square root of n. So the formula here is a little bit easier, at least initially. Okay, so let's look at an example. A publishing company has just published a new college textbook. Before the company decides the price at which to sell this textbook, it wants to know the average price of all such textbooks in the market. The research department at the company took a sample of 25 comparable books and found a mean price of 145 with a standard deviation of 28. What is the point estimate for the mean price of all such textbooks? Okay, well, the point estimate for mu is that mu is approximately 145. And I get that because x bar is 145. My best estimate for mu is that mu is approximately 145. Okay. What is the 90% confidence interval for the mean price of all such textbooks? Now, truth be told, since I only know S, there is an adjustment that as we keep moving through statistics, we're going to make. For right now, I'm going to overlook what's called a t distribution, and we're going to stick with the z value. So I know that mu, my interval estimate, is that mu is going to be somewhere between the 145 minus a margin of error and 145 plus a margin of error. Okay, so what's the margin of error? The margin of error is z sub c, 1.645, and that's 1.645 because we want a 90% confidence interval. Okay, times s divided by the square root of n. So our margin of error, again taking my calculator, 1.645 times 28 divided by the square root of 25, we get 9.2. I'm going one decimal place in this case. Let's go two decimal places, 9.21. So I would expect that mu, one way to write this, is approximately 145 plus or minus 9.21. $145 plus or minus $9.21. Or I can write that mu is somewhere between 145 minus 921, 145 plus 921. And so that's going to be 135.79 and should be 154.21. So my point estimate for mu is that mu is approximately $145. The mean price for all such textbooks I would expect to be approximately $145 plus or minus 921. So mu, my interval estimate, I would expect is somewhere between 135.79 and 154.21, and again, with 90% confidence. This question I have here, what would happen to the confidence interval if we increased the level of confidence or the sample size? Okay, it should make sense. If you increase your sample size, if n increases, your margin of error drops. Okay, if you increase your confidence level, your z value increases, your margin of error would increase. Okay, so those have inverse effects on the confidence interval, which is something that we will explore in the future. Okay, now paired differences. I'm going to speak very quickly on the paired differences because really what you do in a paired differences situation, suppose you're going to do a study on, I think I have an example here of weight gain, right? I'm just going to talk through this rather than do the example, but I take a freshman who goes to college and I wonder what the amount of weight is a freshman gains when they go to college. So I have a group of 50 freshmen. 60 freshmen that are going to participate in the survey. They come on campus, I weigh them, so I have their before weight. At the end of the first semester, I weigh them again, and I have their after weight. So what I'll do is simply subtract the end of the semester weight from the beginning of the semester weight, and I have one score for each person. If I now find the mean of those weights, I have an X bar sub D, okay, a sample mean of the differences. And I would have an S sub D, a standard deviation of the differences. With that information, I would do a confidence interval, and I would expect that mu D would be approximately equal to X bar sub D, okay? And sigma D would be approximately S sub D. And I run this example just like the one I did above. Okay, so again, future videos, future classes, we'll talk about this a little bit more in depth. The last situation I want to run in front of you is the difference in two sample means, because this one is a little bit different. So again, I want to see if there's a difference in the two population means. I'm going to use the sample means X bar 1, mean of the first group, and X bar 2, the mean of the second group, as well as the standard deviations sigma and S from the first and second group. Okay. Some conditions: the two samples must be independent, come from two different populations. Okay. Either the population this comes from is bell-shaped, so this is okay to use, or your sample size is large enough that whether the population is normally distributed or not, the sample would be. And large enough really means that your sample size is at least 30. Now, the formula for the standard deviation seems to explode compared to the previous one, but think about this. Before we had the standard deviation, okay, was sigma over the square root of n. That really is the same as the square root of sigma squared over n. Okay, it's just been simplified. So the fact that now the standard deviation for the difference is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 shouldn't seem that dramatic. Okay, so let's do an example. What's the fastest that you've ever driven a car? Excuse me. So we've got two groups. We've got males and females. And in the survey, males and females were surveyed, asked what's the fastest you've driven a car. We'll call the males group 1, only because they're listed first, and the females group 2. Okay, so N1 is 87 because 87 males were surveyed. X bar 1 is 107. For females, 102 females were surveyed, and the mean fastest time they've ever driven is 88 miles an hour. Okay, so notice that X bar 1 minus X bar 2, 107 minus 88 is 19. Therefore, our point estimate for mu1 minus mu2 is that the difference in the fastest speed driven, on average, for men and women is approximately 19 miles per hour. Okay. Now we're going to make a supposition. Suppose the standard deviations for each population of speeds is known to be 15. So we're working under an assumption here, and that's okay for now, that the standard deviation, population standard deviation for both men and women is 15. So to calculate the standard deviation for the difference is going to be the square root of 15 squared over 87 plus 15 squared over 102. And where I got those from is, remember, that's the square root of sigma 1 squared over n1 plus sigma 2 squared over N2. And that value comes out to be, do that on your calculator. Oh, it's done over here on this on the example on the screen. Run that through your calculator. You should get 2.2. Okay. Oops, sorry. Now remember that your margin of error is still Z sub C times the standard deviation. So if I want to say, and I guess I didn't type all the words out here, let's find another 95% confidence interval. So if I want the 95% confidence interval, Z is going to be 1.96 again. And we're going to multiply that by the 2.2. And so we've got 1.96 times 2.2 is 4.3. So in other words, we would say that the interval estimate for mu1 minus mu2 is approximately 19 miles an hour plus or minus 4.3. I prefer to write that mu1 minus mu2 is somewhere between 19 minus 4.3 and 19 plus 4.3. Okay, so that's going to be 14.7 and 23.3. So my point estimate for the difference between the fastest speeds driven is 19 miles an hour. The interval estimate is that the difference is somewhere between 14.7 and 23.3 miles per hour. Okay, so there's a quick look at confidence intervals and how to calculate those directly using the formulas. Look for my other videos that I have on how to use the built-in feature in the calculator for making those estimates.